Subtraction. It's the process of taking things away. This is, of course, something we learned in grade school. We also quickly learned that this intuitive picture breaks a bit when you try to subtract bigger numbers from smaller numbers. Now, in this case, we know subtracting is the same thing as adding a negative. We can cancel out pairs of positives and negatives, and we're left with our answer. So, subtracting a bigger number from a smaller number gives you a negative. This seems obvious, almost condescendingly so. But this goes to show something really important. If we want subtraction to work in general, what we really need are negative numbers. But how do we get these? Now, typically in introductory ECE classes, when we're learning about how computer numbers work, we're presented with the 2's complement number system. This is basically a way to represent well, that's 2's complement with an I. I meant 2's complement with an E. Thanks though, I guess. Anyways, we have the goal of easy subtraction, and computers, of course, work with binary numbers. These intro classes make it seem like these ideas are inextricably linked to give you 2's complement. Like, if you use binary arithmetic, well then of course you get easy subtraction. That's just the magic of binary. Well, the reality is, while the ideas do go a bit hand in hand, they are also distinct. Easy subtraction is actually more a consequence of modular arithmetic, and binary numbers are useful because it's easy to build circuits that work with them. These two ideas come together to give us the 2's complement number system, but easy subtraction can actually be done in any number system. It's just easier to do in the binary system. I'll get to all these things later. I just wanted to make the point that I'm going to try and not confuse the contributions of these two areas. Note that if you don't know what the 2's complement number system is, well, great. I'll go over it later, but you're luckily starting with a fresh mindset. Now, before we begin, I want to make a quick note that for the sake of convenient language, I'm treating 0 as a positive number. That's not only not rigorous, it's mathematically incorrect. That said, I don't want to keep saying non-negative all the time because, frankly, it just doesn't really roll off the tongue. Honestly, I wish 0 were considered a natural number because then we'd have a pithy term for positive numbers including 0. I guess what would we call negative numbers including 0? Well, I digress here. In this particular case, my sloppiness of terminology doesn't actually lead to any incorrect conclusions, so I think we'll be okay. So moving on, let's talk about how we're going to go about this whole thing. We'll start by talking about how we meaning like people, represent numbers. Then we'll talk about how we represent negative numbers and why this method actually sucks for computing things. That'll motivate us to think about what a negative number actually is. We'll then sort of take a hard turn and talk about how numbers work on a computer, because they have a very unique property that we'll be able to exploit. And no, that property isn't the fact that they're represented in binary. Anyways, that'll lead us to discussing modular arithmetic, and really that's going to be the star of tonight's show. We'll go over the basics of it, and we'll particularly talk about how negative numbers work in this system, and it'll be based on how we decided to rethink negative numbers before. Once we've established the mathematical theory, we can start talking about how computers exploit it. This is the point where the fact that computers use binary numbers will actually come into play. We'll see that there are some neat things about the base 2 number system that let us easily put the theory into practice. It'll naturally lead us to the question of whether the computer can occasionally give us the wrong answers. And to those of you who are familiar with, computery stuff, you're probably thinking of Overflow right now. And you're probably thinking that the answer to the question is, well, yes, occasionally the computer can give the wrong answer. Well, you are right that I'm going to talk about Overflow. But the truth is that mathematically speaking, the computer actually never gives the wrong answer. Practically speaking, though, it does. And I'll go over what I mean by that in detail. And, well, this is basically going to be our journey throughout the whole video. We'll come back to this map every now and then. And with that, there's no better place to start than at the top. So let's talk about how we write numbers. Take a number like 423. What do we mean when we write a number like this? Well, we have 4 times 100 plus 2 times 10 plus 3 times 1. You probably know these as the hundreds, tens, and ones places. If we write it in powers of 10, we see a pattern here. Note that since we're expressing the number 423 in terms of digits, this is its digital representation. We're so used to calling computers digital electronics that I think we kind of assume that the word digital only applies to binary numbers, ones and zeros. That's not really true. Well, in any case, let's consider a generic n-digit number in base 10. This is the number system that we're familiar with. Each digit can take on the values 0 through 9, and each digit is scaled by increasing powers of 10. We can express this more compactly using summation notation. Now, we're trying to think about numbers a bit more generally, so Let's generalize even this a bit further to an arbitrary base, b. Now every digit goes from 0 through b minus 1, and they're all scaled by increasing powers of b. Again, this can be captured succinctly via summation notation. Note that any natural number can be used in place of b. Computers use a base of b equals 2. We, as I said, use a base of b equals 10. And programmers often like writing things down in hexadecimal, that is, in base b equals 16. Now, I don't know enough number theory to say whether it's meaningful to plug in negatives or irrationals for b, so let's just leave that for someone else to explain. In any case, let's take a moment to notice something odd. I said before that we're after negative numbers. Well, we're assuming b is positive, right? 2, 10, 16, whatever. So b raised to any power, well, that's going to still be positive. Now, the digits can only take on positive values, 0 through b minus 1. So basically, this whole summation evaluates to a positive number. This is not some kind of mistake I've made, by the way. It's true that digital numbers can only express positive quantities. So where do negative numbers come from? Well, let's again take the number 423. How would you write down the negative of this number? It's not a trick question. How would you do it? Well, you just put a minus sign in front of it, right? Well, that's actually known as the sign magnitude way of expressing numbers. The 423 is the magnitude. It tells us, I guess you could call it, how much number there is. And the sign tells us whether this amount is positive or negative. Again, digital numbers inherently express positive quantities only. We need to tack on some extra information to convey negative numbers. And that extra information comes in the form of the sign. You can think about this visually as well. The magnitude part tells you how far the number is from 0 on the number line. But we could go 423 steps either to the left or the right. The sign gives us the extra information that we need to tell us that we're going 423 steps to the left. This seems like a pretty decent number system. After all, it works for you and me, right? Well, actually, when it comes to computing things, it kind of sucks. To show you, let's subtract 33 from 14. Well, I mean, you might just think, well, let's go for it and do that column-wise subtraction method that they taught us in class, but it doesn't work. I mean, you can subtract 3 from the 4 and the 1s column, but I mean, what do you even do in the 10s column here? I mean, 1 minus 3, that's a negative 2. Well, the answer is definitely not negative 21, so this isn't working. All right, well, subtraction is adding a negative. Could that help? Well, I mean, again, we set up the column-wise method, but look, I'm not even sure what to do here. The column-wise method for subtraction really only works if the top number is bigger than the bottom one. So what we really have to do is pull a trick. We can write the problem as positive 14 plus negative 33, right? Well, we can then factor out a negative 1, i.e. the negative sign. It then allows us to flip the sign of the things being added. What that means is we've actually flipped the order of the subtraction. Now we're subtracting a smaller number from a bigger number. We just have to remember to negate the result at the end. Now we can actually set up the column-wise method, do the borrowing, and get the answer. Now again, 18 isn't the answer to the original question, it's the answer to that inner subtraction there. So if we reattach the minus sign that we had originally factored out, we get the actual answer, negative 18. Now, this might not have seemed that bad because, I mean, this is how we've subtracted numbers our whole life. But let's take a step back and think about the big picture. When we're working with numbers in sign magnitude form, how do we compute x plus y? Note that this encompasses addition and subtraction depending on the signs of x and y. Well, first we have to check if x and y have the same sign. They can both be positive or they can both be negative. In either case, you add their magnitudes, and the sign of the result stays the same. That is, it's the sign of whatever x and y had before. Now, if they don't have the same sign, we need to ask, does x have the larger magnitude? If so, we subtract the magnitude of y from the magnitude of x, and then the result has the same sign as whatever x had. If x didn't have the larger magnitude, then we subtract the magnitude of x from the magnitude of y, and the result will have the same sign as whatever y had. Now, what's interesting here is that the fundamental operation we perform depends on the signs of the numbers. When they have the same sign, even if both are negative, we add the magnitudes. Whenever they had different signs, we had to subtract the magnitudes. And we also needed to do some extra thinking to choose which one gets subtracted from what. Now, again, This seems condescendingly obvious, especially because, as I said, you already do this. If we could look inside your brain every time you did a simple math problem, odds are this is exactly what your thinking process is. Okay, let me put that back. Sorry about that. Anyways, we'll later see that when we consider an alternative representation of negative numbers, all we ever need to do is add numbers, and we don't have to care about the signs at all. The first step to doing this is to rethink what a negative number is. It's not just a number that goes in a different direction than its positive counterpart. Let's think about what a negative number is in terms of what it does. Intuitively, the negative of a number is just some other number that cancels out the first one. Mathematically speaking, for any x, if there's a number y such that x plus y is 0, then y is the negative of x. Note that since x also canceled out y, x is also the negative of y. They're both negatives of each other, basically. If you've taken group theory before, this is how the inverse of an element is defined, more or less. We think about its relationship to the other elements rather than thinking about what exactly this element is. If you haven't taken group theory before, don't worry, it's not going to be on the test. Also, there's not going to be a test. Well, that was a super short stop, but it was of crucial importance. Let's now think about how numbers work on a computer. And again, I don't mean the fact that they're in binary. That's not important yet. No, what's really important about computers is that every number has to use a fixed and finite number of digits. It's funny because, that actually sounds like a limitation, and, for the most part it is. It places limits on what we can compute and to what precision, but funnily enough, it's actually going to be the thing that saves us from this sign magnitude representation, which, if you recall from the flowchart, it sucks. Let's see how this helps out. Well, let's suppose that we're working with numbers in base 10 and that we have 2 digits and 2 digits only. No more, no less. We can easily represent numbers like 7 or 24. We can also count all the way up to 99. What happens if we try to count further? Well, after 99 comes 100. But to represent 100, we'd need a third digit. And I said that you only get 2 digits. So that leading 1 actually doesn't exist. So what that means is we've counted from 99 and wrapped back around to 0. This is a unique numerical structure imposed by our constraint on the number of digits. This structure is the integers modulo 100, which we often write as z mod 100. We can keep counting on some more. If we go 6 ahead, we should be at 106, but we're really at just 6. So this wrapping around goes on and on and on. Now, we can generalize this wrapping around behavior to an arbitrary, but again, fixed number of digits in an arbitrary base. For instance, let's take a number with n fixed digits in some base b. What mod group are these numbers from? Well, let's fill each digit with the highest value that we can, which again, in base b is b minus 1. If we add 1 to this number, we get 0 in the first digit and we carry over the 1, which gives us 0 in the second digit and carries over another 1, and well, so on until we get a 1 way out front. Now, remember from our discussion on the digital representation of numbers that each digit scales various powers of the base b. That last digit scales b to the n. However, we know that that 1 can't exist because we only have n digits, no more, no less. So by hitting b to the n, we've wrapped around to 0. So the structure imposed is z mod b to the n. Now, you might wonder what any of this has to do with a computer, since computers work in base 2. But remember, that wasn't the important part. The important part was the fact that numbers in computers have a fixed and finite number of digits. So to talk about that properly, there's no need to restrict our discussions to base 2. Now, I want to take a brief aside to derive a mathematical fact that we're going to go and keep in our back pockets. Suppose, again, that we have n digits in base b. We'll use m to refer to the modulus. That is, these numbers are from z mod m. Now, we saw previously that m is equal to b to the n. Now, if we load every digit with the highest possible value and we add 1, we saw that we get b to the n, which is, again, the modulus m. Now, let's ignore for now the fact that this wrapped around to 0. If we take that 1 and we move it to the other side, we see that maxing out all the digits gives us b to the n minus 1, i.e. it gives us the modulus m minus 1. Now, it's that second part that's really important, and I'll remind you of it when it comes relevant later. Why am I bringing it up now at all? Well, again, I want it to be clear that this mathematical fact has nothing to do with binary numbers or base 2. This is just a general number theory fact. Okay, so the restrictions placed on numbers, right, fixed finite number of digits, it's led us to a very cool subfield of number theory, modular arithmetic. We're going to think a little bit more abstractly about numbers here, right? So this digital representation of numbers, it's exactly that, a representation. We're going to drop that view, and we're not going to talk about digits anymore. We're just going to speak about numbers as they truly are. So for the sake of working with something concrete, let's use a particular mod group, Z mod 8. Rather than a number line, modular arithmetic is performed on a number wheel. There are 8 spokes on this wheel, corresponding to the fact that the modulus is 8. Trying to count from 7 to 8 makes you wrap around to 0, which is what makes 8 the modulus. Now, if you're looking at this, you might think that numbers such as 8, 9, 10, and so on, well, these are just works of the devil. I mean, how can there be a number larger than 7 when, it's not even on the number wheel? Well, the truth is, all those numbers are there. They're just stacked on top. You can indeed count up to 8. It's just that 8 is on top of the 0. From there, you can go on to 9, which is atop the 1. 10 is atop the 2, and you can keep going all the way around and then around again, and you can keep going on forever. So all the numbers still exist here, but they're just on one of the 8 different spokes on the number wheel. All the numbers in one spoke, by the way, are considered a congruence class. The numbers inside a congruence class are all essentially identical, and so we say that they are congruent. Note that they aren't equal. They're different numbers. It's just that their behavior in this number system is identical. That's why we use a symbol that's different than the equal sign. It's also important to note that, well, they're only congruent in mod 8 space, in this particular number wheel. On some other number wheel, you can imagine that the numbers, as they wind around, well, they'll stack up differently, right? So the numbers in a congruence class would be completely different. So what we do is when we're expressing congruence, we tack on a mod 8 at the end, or whatever the modulus that we're considering at the time is, and that indicates that the numbers that are congruent, well, they're only congruent in the modulus that we're working with. Well, now that we have that, let's make the idea of congruence a little bit more precise, and we'll also consider it more generally. We'll say we're working with numbers from Z mod m, where m is some arbitrary modulus. Now, m is always congruent to 0 in mod m. This is probably the most recognizable feature of mod m space. Now, we say that two numbers a and b are congruent mod m if and only if m divides b minus a. That's equivalent to saying that you can add some multiple of m to a in order to get b. It's also equivalent to saying that dividing b by m gives you a remainder of a. But for this definition to work, you need to assume that b is greater than a and that a is between 0 and m. All right, now let's look back at Z mod 8 to make these ideas concrete. Look at the congruence class that 3 is in. We see visually that 3 and 19 are congruent mod 8. You can show this mathematically by subtracting 3 from 19, which gives you 16, which the modulus 8 divides. Alternatively, you can add some multiple of 8 to 3 to get 19. And finally, dividing 19 by 8 gives you a remainder of 3. These facts are essentially just different ways of saying that you can start at any number in a congruence class and get to all the other ones by either adding or subtracting the modulus from it. Okay, now there's a lot of numbers on this wheel, but truth be told, we often just work with the smallest ones. This is known as the least residue system. So we can discard all the other numbers, but it's worth remembering that they are all still there. Now before we move on, let's talk about addition in this number system. Well, addition just corresponds to moving around the number wheel. For instance, 7 plus 1 is equal to 8, but 8 is congruent to 0 mod 8. So 7 plus 1 is congruent to 0. That's consistent with walking one space clockwise or forward from 7. The result of the addition is congruent to where we end up on the number wheel. So if we do 7 plus 3, this is equal to 10. But 10 is congruent to 2 mod 8, and so 7 plus 3 is congruent to 2 mod 8. And that's exactly where we land if we walk 3 spaces clockwise or forward. Now, we can add negative numbers too. You just walk the other direction. For instance, 4 minus 3 is 1. And since 4 minus 3 is the same as 4 plus negative 3, then 4 plus negative 3 is congruent to 1 mod 8. This is consistent with walking 3 spaces counterclockwise or backwards from 4. Again, adding a negative is still just walking around the number wheel, which means subtracting is also just walking around the number wheel. Okay, now that we've introduced ourselves to the number wheel, let's get back to the task at hand and talk about negative numbers, specifically in the context of modular arithmetic. Remember, we said that the negative of a number is just some other number that cancels out the first. So let's start with 3. Negative 3 is what you add to 3 to cancel it out. We see this must be true because if we walk 3 steps counterclockwise from 3, well, we end up at 0, right? So adding negative 3 to 3 gives us 0. Cool, that seems pretty obvious. But now, let's suppose that we instead walk 5 steps clockwise. That is, we'll add 5 to 3. Well, I mean, this takes us to 0 as well. 3 plus 5 must be congruent to 0. Well, that means that positive 5 must also be the negative of 3 as well. Since both negative 3 and 5 cancel out 3, they really must be congruent. And this is a huge win because remember, congruence means that the objects behave exactly the same. In this mod space, they're essentially indistinguishable. And here, we have that a positive and negative number are the same thing. Now, this congruence, what it intuitively means is that in terms of the number wheel, going backwards 3 steps is the same as going forward 5 steps. So this idea that a positive number and a negative number can be congruent, well, this is because we're exploiting a property inherent to the number wheel. You can go backwards by going forwards. If we think about the number line, the thing we're more familiar with, this is absolutely not true. The number line stretches infinitely in both directions. So going forward will just never take you backward. And so the negative numbers are just entirely separate things that we had to deal with. Now, it might seem like I've pulled a rabbit out of a hat here. Well, the reality is that the negative numbers were actually here on the number wheel the whole time. I just actually hid them from you for the sake of shock value. Remember how we wound around the number wheel clockwise to get all the positive numbers? Well, there was no reason that we couldn't have wound around the other way to get the negative numbers. If we go backwards, we get negative 1 stacked on top of 7, negative 2 stacked on top of 6, and we can go around and around just as before. Notice that negative 3 and 5 are in the same congruence class, just as we saw before. So these 8 numbers of the number wheel, the least residue class, these represent all the positive and all the negative numbers at the same time. Truly remarkable. Okay, it's now time to make negative numbers a little bit more precise. We'll take any number x from z mod m. Take m minus x, which is also from z mod m. You'll see that if you add x and m minus x, you're left with just m, which is congruent to 0 mod m. Since adding m minus x to x canceled it out, m minus x must be congruent to the negative of x, mod m. It's worth emphasizing that if you have some x and you want to make it negative, you just subtract it from m, and that number that you get, that is the negative of x. How can we use this fact? Well, take some x and some other number y from z mod m. We know that negative y is congruent to m minus y mod m. So take x minus y, a subtraction problem. This is the same as x plus negative y. Now, we know that negative y is congruent to m minus y, so that subtraction is congruent to x plus m minus y mod m. Now, of course, on the surface, this seems like a useless transformation. But, notice that the original subtraction has now been replaced with addition. So remember that in the sign magnitude case, we had 2 different kinds of operations that we had to perform, sometimes addition, sometimes subtraction. Well, in modular arithmetic, we only need to do one operation, addition. Okay, let's hold on a second here. This is one of the main points in the video, so it's worth making sure that we don't leave any stone unturned. And one big rock that's sitting right in the middle of this screen is, why did we need to replace negative y with m minus y? We had already turned subtraction into addition when we said we were adding negative y. What use is this congruence? Well, yes, converting to addition is important, but that isn't enough. Remember that eventually we're going to be working with digital numbers. And we saw way back that inherently digital numbers can only represent positive quantities. Earlier, we got around this by tacking on extra information, specifically in the form of a sign in front of the number. But we don't want to do that. We don't want to rely on tacking on extra information because having numbers composed of 2 parts like that is what led to us having to go through this flow chart when computing x plus y. Here, x and m minus y are both positive quantities. What that means is that every computation can be expressed in terms of adding positive numbers. So there is no flow chart that we have to go through. Let's go through a quick example to emphasize that last point. We'll work in a space where the modulus is 8. Now, what we'll do is we'll make a table with the possible values on the x and y axes, and we'll fill the table with the values of x plus y mod 8. Notice that all we're looking at are positive values. Let's look at where all the zeros are on this table. And, well, hey, look, it's a line. And it's not just any line, but the line 8 minus x, or rather, m minus x. And remember, m minus x is congruent to negative x. So this is the linear equation of y congruent to negative x in mod 8. We can use this line to find the negative of any number. Take 3. If we go up from the cell to the cell containing 0, we can find out what the number we had to add to 3 to get 0 was. And if we go to the left, we see that it appears to be 5. So the negative of 3 must be 5. Note that we could have started at the 5, gone to the right, and then gone down to see that the negative of 5 is 3. And we could have also used the other 5s and 3s on the axes. Negatives come in pairs, and addition is commutative, so our usage of this table gets some wiggle room. Okay, now, let's solve an actual problem. What is 4 minus 6? Well, let's rewrite it as 4 plus negative 6, right? So subtraction can become addition. We just need to find some other positive number y that's congruent to negative 6. And then our subtraction becomes the addition of two positives. Okay, so how do we find y? Well, we're trying to find the negative of 6, so start at the 6, go up to 0, and then left to 2. What that means is that 2 plus 6 equals 0. So 2 must be the negative of 6. So y is 2. 4 plus y then becomes 4 plus 2. And then we can use the table again to find out that 4 plus 2 is 6. Now, I'm sure you could have done that last step in your head, but the point is to make all the computations transparent here. So what does this all mean? It means that 4 minus 6 is congruent to 6. Now, 4 minus 6 is directly equal to negative 2. But we already saw that negative 2 and 6 are congruent. So we indeed got the correct answer here. And again, the thing to notice about all this is we only ever performed computations with positive numbers. And the only computation we performed was addition. Now, that said, there was kind of a whole song and dance that we had to go through to turn negative 6 into positive 2. And that really is the last thorn in our side when it comes to doing subtraction easily. Now, the truth is, your computer doesn't actually use a lookup table like this. It would take up way too much memory to be practical. The table here, purely pedagogical. In reality, computers will use this procedure. To negate a number x, it'll subtract it from the modulus m. So, to do subtraction, it has to do subtraction? Well, kind of looks like we've gone in circles here. And indeed, m minus x is annoying to have to compute, except when you're working with a finite number of digits that are in base 2. And, well, oh yeah, that's exactly what computers do. So our detour into pure math land is now over. Let's start talking about computers again. And yes, now binary actually becomes relevant. Now, we're going to be talking about digital representations again, so let's get our bearings back. We know what n-digit numbers look like in base b. Well, computers, again, do all this, but they use a specific value of b, 2. Now, every digit can only take on one of two values, 0 or 1. So numbers are constructed from these binary digits, aka bits. So this is really an n-bit number. Now, remember these neat little number facts that we derived? Well, we'll again specialize them for base 2. And remember, it's only that second one that's really important right now. Now, essentially what it says is that a binary number with all ones as its digits is the modulus minus 1. And again, I presented it way back because I wanted to make it clear that this isn't a property unique to the binary number system, it's just how numbers work. But now we're going to see that this fact comes very much in handy. Let's take a 4-bit number. What mod group is this from? The base is 2, we have 4 digits, so the modulus m is 2 to the 4, or 16. That means we're working in z mod 16. Now, let's pick some arbitrary number. I'm showing 6, but this can really be any number you like. Let's now flip the bits, meaning that ones become zeros and vice versa. Well, if we add the two numbers together, we're going to get all ones. And that, of course, makes sense because in every column, there's exactly 1 0 and 1 1. Now, remember from our neat little number facts that this number with all ones, it's equal to the modulus minus 1. Adding these two numbers gave us m minus 1. It may not be obvious, but this is huge, and we're about to see why. Let's suppose we have some arbitrary n-bit number x. We saw that x is from the mod group with modulus m, where again, m is 2 to the n, but actually we don't care about the value of the modulus here. Now, let's use squiggly x to denote x with its bits flipped. There's an example in the upper right corner if you kind of want to see what this looks like. Well, as we saw before, x plus squiggly x gives us all ones. And again, feel free to confirm with the example in the upper right corner. We know that all ones gives us the modulus minus 1. Well, let's switch some terms around. Squiggly x plus 1 is equal to m minus x. We know from before that m minus x is congruent to negative x. Thus, flipping the bits of a binary number x and then adding 1 gives you a number that's congruent to the negative of x. And that right there is 2's complement, y'all. Now, we've looked at so many freaking equations, honestly, that this seems like just another one to toss on the pile. But this one is particularly neat in the context of digital circuits. There's a component in digital circuits that you may have already heard of. It's called a NOT gate. I'm showing you here what they look like schematically. The idea is that if you put a bit, a binary digit at the input, you get the flipped version of that bit at the output. Zeros become ones and vice versa. Now, this isn't a video on digital logic design or circuit theory, so I kind of don't want to get into like how NOT gates work or how they're used and all that kind of stuff. The takeaway here is that flipping the bits, well, that's super easy to do in a digital circuit. What that means is that negating numbers is easy to do in a digital circuit. Remember, mathematically, we have a way of taking any positive number and turning it into another positive number that acts like the negative of the first one. The problem was that this conversion seemed like it was going to be super annoying to do. But if you stick with binary numbers, it's actually super easy to build a circuit to do it. Now, it's worth mentioning that this trick of, flipping the bits and adding 1, it does have a generic analog. Take an arbitrary n-digit number in some base b. We'll form a new number from this first one by subtracting each digit from the largest digit possible, which again is b minus 1. We then end up with a number that, by construction, is something that you add to the first one to get another one with the digits all maxed out, which, of course, is equal to the modulus minus 1. Now again, when the base b is 2, the weird digit conversion thing here, well, that just becomes 1 minus little d sub I, which of course is just a bit flip that can be implemented with a NOT gate. If we were working in, say, base 4 arithmetic, we make the new number by doing 3 minus little d sub I. That's no longer a simple flip, but some kind of permutation of the digits, and well, that seems a lot harder to do. So again, the fact that we're in base b equals 2 just makes this procedure easy. All right, now, I think we've done enough theory. Let's try out an example. Let's do 7 minus 3. We'll use 4-bit numbers for this, so we're working in Z mod 16. We want to replace subtraction with addition, so instead of subtracting 3, we'll add negative 3. What does this look like in binary? Well, we know what 3 looks like in binary. We can then flip the bits and add 1. We now have the binary representation of negative 3, and we can use that in our computation. Now, if you interpret these bits literally, this is the number 13. Why are we adding 13? Well, 13 and negative 3 are congruent modulo 16. And remember, congruence means that these numbers act like the same number. So adding 13 is indistinguishable from adding negative 3. If we do the addition, we end up with 4. And, well, yeah, 7 minus 3 is indeed 4. Let's now do 2 minus 3. If we do the addition on the right, we get all ones. Now, again, if you interpret the bits literally, this looks like 15. But 15 and negative 1 are congruent modulo 16. So our answer is actually negative 1. Again, I want to emphasize that 15 is negative 1, at least in this mod 16 space. They're congruent. We can actually see this by adding 1 in both cases. We'll see that we end up with 0. Now, what if we replace negative 1 with 15? Now if we add 1, we get 16. But 16 is just 0 mod 16. So again, the end result is the same. Okay, now I want to take a little bit of time to connect these ideas with something that's commonly taught to ECE students. It's just like one last loose end to tie up. And this is that there's another way to interpret the 2's complement number system. Basically, the weight of the last digit, it isn't 2 to the n minus 1, but rather negative 2 to the n minus 1. Where does this come from? Well, let's again take a 4-digit number. We'll put all ones in every digit except the biggest one, the leading digit. This, of course, is equal to 7. Now, if we flip the bits and add 1, we get the representation for negative 7. Now, let's subtract 1. We end up with -8. And the number has a single 1 in the largest digit place. So it's almost like that digit has a negative weight, a weight of -8. Now, this is actually a convenient way of thinking about 2's complement numbers because it gives us an easy test for whether a number is negative or not. Just look and see if there's a 1 in the largest digit. Now, all the other digits combined don't add up to the weight of that negative weighted digit. In this case, they only add up to 7. And so with all the digits as 1s, you end up with -1, right? So those little digits weren't able to overwhelm the largest digit. So basically what that means is this test is never wrong. If there is a 1 in the largest digit's place, you're basically guaranteed that the number is negative. And since it's the only digit with negative weight, if there's a 0 in there, you know the number is positive. All right, so now we pretty much know everything we need to know about how computers use negative numbers. Well, almost. There's an elephant in the room that we have to address, and it's the issue of overflow, which can make it seem like the computer spits out wrong answers sometimes. As I said before, in my opinion, this is a practical way to view things, sure, but it's mathematically incorrect, or at least maybe misguided. Let me explain. We'll focus on adding 4-bit numbers, which come from CMod 16, but I should mention that what we're going to talk about here generalizes to numbers of any size, including the 32 and 64-bit numbers that your computer normally works with. Now, we don't care about all the digits, but let's say that we've got zeros in the leading digit. What that means is that these two numbers are positive. Now, suppose that when we're adding the numbers, the lower digits are such that we end up with a carryover. So when we add these two numbers together, we'll end up with a 1 in the leading digit of the sum, which means that the result is negative. Adding two positive numbers gave us a negative. Programmers call this overflow, and they consider it a wrong result. Let's see an example. We'll add 5 and 3 together. If we do the addition, we'll see that we end up with -8. Uh-oh, overflow. That's the wrong answer. Well, or is it? Sure, 5 plus 3 is equal to 8, which is not equal to -8, but it is congruent to -8, at least in mod 16 space. So 3 plus 5 is indeed congruent to -8. The computer wasn't wrong, mathematically speaking. We have to remember that we're working in mod 16 space. We're interpreting the result incorrectly by thinking that 8 and -8 are distinct objects. Now, we can have a similar situation, another kind of overflow, where we add numbers that have 1s in the leading digit, but we don't get any carryover from adding the lower digits. In this case, we'll end up with a 0 in the leading digit of the result, and so adding two negatives gives a positive. Again, overflow. As an example, consider adding -5 and -4. The result is 7. Is this wrong? Nope. -5 plus -4 is -9, which again, it's not equal to 7, but it is congruent to 7 in mod 16 space. So -5 plus -4 is indeed congruent to -7. The computer didn't give the wrong answer. Rather, we interpreted the answer incorrectly by coming in with the assumption that 7 and -9 are distinct objects. But again, we're really working in mod 16 space where they're the same thing. So these issues of overflow are a practical one rather than a mathematical one. If you decide to eschew the view that we're working with the number wheel, and you instead think about everything in terms of the number line, then sure, yeah, the ghost of integer overflow will haunt you. But if you embrace the mathematical structure that's imposed by computers, then integer overflow, well, it's just a thing that's in our heads. So, don't forget the number wheel. But, like we also use computers to model the real world, which, relies on non-modular arithmetic. So overflow is very much a real pain in the ass of programmers everywhere, so please watch out for it. Anywho, that basically concludes our journey. It was a super long one to say the least. I'm sure you came into this video knowing how the computer giveth. Hopefully now it's clear how it taketh away.